Hello everybody, we start at the point that we finished last time in the middle of the Debye model. Okay, I'll just remind you where we are standing. Okay, so we managed to calculate the following things. First of all, we calculated the d of omega. Okay. What is the d of omega? It's the density of states with a specific frequency omega for the standing waves inside a media, and it was v divided by 2 pi squared, what we had over here, 1 over c tilde to the power 3, okay, omega squared. I'm just reminding you that 1 over c tilde to the third was 1 over c longitudinal to the third plus 2 of c transversal to the third. Okay. So this is the effective, I can say, this is the 1 over the third power of the effective speed of propagation of those waves. Another thing is that we calculated omega Debye. What we mean by omega Debye. So our spectrum was as follows. So d of omega went exactly like this, right? So this is d of omega. But we had a cutoff. Remember, the cutoff appeared due to the assumptions of Debye that were based on the following fact. We are looking on waves inside matter, and at some point we have an interatomic separation. So there is nothing that can oscillate or perform a wavy motion in between the atoms. So there should be a wave. Okay? Now there was an assumption of Debye that the dispersion relation between the wave vector and the frequency, okay, is simply linear, right, up to a specific point, which is this cutoff. We know that this is not true in nature, but this is part of the model. So d of omega reforms exactly like this. Okay, so it goes as omega squared up to this specific cutoff that happens at omega Debye, and it's 0 afterwards. So this is the density of states, and the omega Debye that we calculated was, let me remember, so it was something like it seems peculiar what I have over here. So it is omega Debye was 18 divided by n divided by, we see the volume, 1 over c tilde, right, 1 over c tilde to the third, and all of this to 1/3. Okay. This is what I have in my notes. I'm missing somewhere pi's over here, right? So it is pi squared over here. Okay. So we stopped at this point, right? Oh, and something else that we have calculated is that z is multiplication over all the possible modes, over possible phonons that we have in our system, z1 of omega, okay, where z1 of omega, it is 1 over 1 minus e minus beta h bar omega. Okay. Where it came from? It came from the fact that we're looking on a phonon, this quasi-particle, as an oscillator. The oscillator can have quantas of energies, 0 h bar omega, 1 h bar omega, 2 h bar omega, etc., etc. We sum this geometric series, we obtain this guy. Now the next fun part is to somehow incorporate inside the distribution of different omegas, this density of states. So what we do, remind you, so for example the free energy was minus 1 over beta log of z, which is simply minus 1 over b, a sum over all possible omegas of, right, because we have a multiplication of log of z of omega, z1 of omega. Okay, so it is minus 1 over beta, sum over omegas, and log of z of omega is what? Is this guy over there. So we can erase the minus, and we have a log of 1 minus e to the power minus beta h bar omega, and here we stopped. Now the next step is to say, well, here we sum up over all possible omegas, over all possible phonons. For each phonon, we summed up over all possible energies, and we obtained this guy. This is coming from the multiplication over all possible modes in the system, or basically counting all the possible phonons inside the system. What a phonon? Oscillation, a specific omega. This is why we're summing up over the omegas over here. And now we can take into account, okay, this d of omega over here. So the free energy is 1 over beta, an integral from 0 to omega dBye, right? This is the limits of our integration, because we know that d omega is starting from 0 and it continues up to omega dBye and 0 afterwards. So we don't care what happens for omegas larger for omega dBye. Here we have a log of 1 minus e minus beta h bar omega. Okay. What else? Multiplied by this d of omega, which is v divided by 2 pi squared 1 over c tilde to the third power omega squared d omega. Okay. This guy over here is our free energy, right? We want to compute something that actually can be measured. For example, the specific heat. What is the specific heat? Okay. Specific heat is du to dt. We can go to the definition of the energy, average energy, take its derivative with respect to the temperature, okay, and count everything what we want. Now, how one computes this average energy? There are several ways. Okay. A, we have already a formula, but if one do not remembers what is the formula, one can always derive it, right? How this formula is related to F. We can start from here, okay, and use the formulas, or I remind you that U is a sum of I, E of EI, right, multiplied by E minus beta EI divided by Z, okay. This is always a formula, no matter what the system is. Okay, then I remind you that we used the following trick. We took 1 over z out of this, okay, and we said that this is a sum of I minus d to d beta e to the minus beta ei, right? This is called the Feynman trick, right? Which is simply equals to 1 over z minus d to d beta of a sum over I e minus beta ei, okay? And the sum over here is simply the partition function. So we have minus 1 over z d to d beta of z, and we obtain this formula that u equals minus, right, minus d to d beta of log of z. So the moment that I know what is log of z, I take the derivative with respect to beta, and I have the average energy in the system. This is the same way as I obtain the free energy. Okay? Now, if I want to take further or compute the specific heat, which is measurable quantity in experiment, I need only to take the derivative with respect to T of this guy. Remember, beta is 1 over K Boltzmann T. Okay, so everything is nice. And I want to continue into the calculation of the energy of the system. Okay. So we are going to compute this guy, the average energy. So u equals minus d to d beta of log of z. So it is simply, again, a sum over omega log of 1 minus e to the power minus beta h bar omega. Okay, and we have a plus over here. Fine? Okay, now again, instead of having a summation over omega, I'm doing an integration. So it is d to d beta, an integral between 0 and omega dBi of a log of 1 minus e to the minus beta h bar omega, okay, multiplied by the same thing that I put inside over here. Okay, this is the d of omega. D of omega, d omega. So we obtain that u equals to d beta of an integration from 0 till omega dBi, okay, of a log of 1 minus e minus beta h bar omega. And here we put all these numbers. It's v divided by 2 pi squared, 1 over c tilde to the third, omega squared, d omega. Okay. So the only thing that's left is to take the derivative. Okay. Right? Anything else that happens over here? Nothing really, right? Okay, so we're now taking the derivative with respect to everything, with respect to beta. So the only thing that matters is this guy over here. So u equals an integral from 0 till omega dBi of 1 over 1 minus e to the power minus beta h bar omega. The internal derivative is e to the power minus beta h bar omega multiplied by minus h bar omega. So we have h bar omega over here, e to the power minus beta h bar omega, v divided by 2 pi squared, 1 over c tilde to the third, omega squared, d omega. Okay. So eventually we are left with one single, we are left with only one single, why is that? I don't know. One single integration. Okay. I haven't forgot anything, I hope. Right? Now, this is very different from whatever we were calculating when we were using Einstein model. Remember, Einstein model, we only had 3n particles. They are completely independent. It was really, really easy. Okay, there was only summations that we had to perform of geometric series, and afterwards taken into some sort of a derivative of that. here we have this u, okay? This is the expression for the energy. If we want to calculate something measurable, we want to explicitly take this CV, okay? Another derivative of this ugly mess, okay? In order to continue. All right, so there are actually no way around this. One have to take derivatives and calculate those integrals. They are not that complicated, right? It's eventually I will show you that we're left with something actually quite nice, and we can explore the behavior in the limits of large temperatures, small temperatures. But for a while, bear with me a little bit till I still dance a little bit around this integral over here. Okay, so next step is simply to take the derivative of this guy. All right. So what I want to tell you, how I'm actually calculating this. So CV is du to dt. And remember, in all those nice places where I have beta, it's actually 1 over k Boltzmann T. 1 over k Boltzmann T. Fine. So it is an integral between 0 and omega dBi, h bar omega. Let's take everything that is independent of beta and put it in the front part of this integral. So we have h bar omega to the third multiplied by the volume divided by 2 pi squared, okay, c tilde to the third, okay, and now we're left with d to dt of e to the power minus h bar omega divided by k Boltzmann T divided by 1 minus e to the power minus h bar omega by k Boltzmann T, okay, d omega. Okay, so what is this guy? D to dt of e to the power minus h bar omega k Boltzmann T divided by 1 minus e minus h bar omega k Boltzmann T. Okay, so let's do this. First of all, let's take the derivative of this guy, which is e to the power minus h bar omega k Boltzmann T multiplied by minus h bar omega divided by k Boltzmann multiplied by 1 minus 1 over t squared, right? All of this divided by 1 minus e to the power minus h bar omega k Boltzmann T, okay, plus e to the power minus h bar omega divided by k Boltzmann T. And here what we have, 1 minus e to the power minus h bar omega k Boltzmann T squared, okay, multiplied by minus 1. I'm taking the derivative of the denominator, okay. Okay, inside we have minus e to the power h bar omega k Boltzmann T. Very nice, yes. Multiplied by the internal derivative of this guy, which is minus h bar omega k Boltzmann T, k Boltzmann, multiplied by minus 1 over t squared. You're happy? Very happy. I'm too extremely happy with all those numbers. Okay. Don't worry, it won't continue that long. Okay, so now we have to take this guy, put it inside, okay, massage it a little bit. You want the final expression? Yeah? No? Okay. This is actually not extremely bad. Why it's not extremely bad? Because you see here in the denominator, I have 1 minus e to the power minus h bar omega k Boltzmann t squared, and I here have only 1 minus e to the minus h bar omega k Boltzmann t. So I take this guy and multiply the numerator and denominator by 1 minus e to the minus h bar omega k Boltzmann t, okay? So this guy is also multiplied by this, 1 minus e to the power e minus beta h bar omega. And then you sum up all those two terms, okay? So there are some factors that are exactly the same, like minus h bar omega k Boltzmann 1 over t squared. The same goes over here. Everything, or not everything, a lot of the stuff is actually cancels out. And eventually we get that CV has an integral from 0 to omega debye of h bar omega to the third v 2 pi squared c tilde to the third. What we have over here is, let me see. Okay, so we definitely have h bar omega divided by k Boltzmann t squared, okay, multiplied by 1 over 1 minus e h bar omega k Boltzmann t squared, okay, and over there we have minus, minus, minus. So here, look, this is 1 minus, 2 minus, 3, 4, so this is plus. And here we have minus 2, this is plus, and multiplied by e to the minus. Okay, so here we only have e to the power minus h bar omega k Boltzmann t. That's it. D omega. Okay? Everybody see it? No, thanks. Okay, this is the last expression. Yes, am I right? Let's see. It seems reasonable. Okay, it seems reasonable. Okay. Very nice. Now, I want to take out of this integral several things that are bothering me, or they are simply not dependent on omega. So we have over here h bar squared v, okay, what else? 2 pi squared c tilde to the third 1 over t k Boltzmann, thank you. So k Boltzmann is 1 over k Boltzmann. What else we have? 1 over t2 squared. And inside we have 0 to omega debye of omega to the fourth e minus h bar omega k Boltzmann t divided by 1 minus e to the power minus h bar omega k Boltzmann t, all of this squared d omega. Okay? The next step is somehow make this integral a little bit more reasonable. Okay? What I mean by a little bit more reasonable? Well, we want basically get rid of all this h bar omega divided by k Boltzmann t, and let's call all of this u. Okay? So h bar omega divided by k Boltzmann t equals u inside the integral, because now it's easier to integrate over something like that. So du equals to h bar, or d omega equals to k Boltzmann t divided by h bar du, okay? Omega equals to h bar u divided by k Boltzmann t. And instead of omega dBi, on the upper limit, we will have something different too. Okay? So CV now equals to h bar v divided by 2 pi squared c tilde to the third 1 over k Boltzmann 1 over t squared integral between 0 and omega dBi. Now instead of omega dBi, okay, what we have h bar u so u goes up to h bar omega dBi divided by k Boltzmann t. Okay. Yep. No. What?
The omega is supposed to be u kBt over h bar.
Yes. Thank you. U k Boltzmann t divided by h bar. Right? Yep. Okay. So we're going up to u dBi. Okay. And what is u dBi? U dBi equals to h bar omega dBi divided by k Boltzmann t. And inside what we have, instead of omega, we have u k Boltzmann t divided by h bar to the fourth power e minus u divided by 1 minus e to the power minus u squared, and instead of d omega we write k Boltzmann t divided by h bar du. Still ugly. Okay. But we are almost there, I hope. Okay. So look at this, and we have that CV equals, let's take whatever is independent of u outside of the integral. So we have CV equals h bar v 2 pi squared c tilde to the third 1 over k Boltzmann 1 over t squared. Here we have k Boltzmann to the fourth, t to the fifth, h bar to the fifth, so everything h bar to the fifth, right? So this is k Boltzmann divided by t, k Boltzmann t divided by h bar to the fifth, okay, multiplied by an integral from 0 till u dBi of e minus u divided by 1 minus e minus u squared du. Oh, this is already nice. Yep. H bar squared over here. Okay, yep. Thank you. Okay. Don't worry, it's going to be over soon, and we'll make another long calculation. But this is not really that awful. Why? Because we are actually finished in calculating the specific heat. Okay, yep, you're right. U to the fourth. You're absolutely right. Yes, I forgot it. So CV, let's look what we have inside. We have h bar to the, forget about. So we have v divided by 2 pi squared c tilde to the third. Okay, now let's deal with all this k bar, k Boltzmann t and h bar. So we have h bar to the third, so k Boltzmann to the third, divided by h bar to the third, multiplied by, no, it's k bar to k Boltzmann to the fourth, h bar to the third and t to the third. Great. Okay, multiplied by an integral from 0 to u debye u to the fourth e minus u divided by minus u squared du. Okay, so this is already something that depends only on T. K Boltzmann H bar, so this guy depends on temperature. Here, U is the integration variable. We don't care about it. The only dependence on temperature comes from where? From UD, exactly. From UD. So UD, okay, is H bar omega debye divided by K Boltzmann T. Now we can have two limits. Let's look on the limit of very small temperatures. Okay, so the limit of T goes to 0. Okay, so when T goes to 0, right, H bar omega debye is a constant, right? Do you remember what omega debye is? We have written it down. So omega debye is some number, okay? Is some number. So it doesn't matter. It's a constant, independent of temperature, okay? Divided by temperature. So when T goes to 0, U debye goes to infinity, okay? It goes to infinity. Yep.
Why does it matter because we have a t to the third?
Yeah. You absolutely no.
It goes to 0.
Sorry. T goes to 0. I don't want. You're saying CV goes to 0. This is right. But remember why we calculating all of this stuff and I'm bothering you with those long calculations. Einstein model failed in the limit of small temperatures. It predicted that the CV goes to 0. This is clear. Okay. The question was how it went to 0. What is the temperature dependence? Okay? In the Einstein model, the temperature dependence was exponential. It went to 0 as e to the some power 1 over t. Okay? And this is wrong. Okay? What is right from the experiment that the temperature dependence is that CV should be proportional to the third power of t in this small temperature limit. And this is what we are trying to achieve. Right? Now, when UD goes to infinity, we have this integral, an integral between 0 and infinity of u to the fourth e minus u divided by 1 minus e minus u to the second power du. This is an integral, but this is a number. Okay? We can call it lambda naught, lambda 0. I don't care what this number is. It's a prefactor. Okay? So what we have obtained that in this limit of small temperatures, in the limit of small temperatures, CV goes as T goes to 0. There is a prefactor. Okay, what is this prefactor? V divided by 2 pi squared C tilde to the third, K Boltzmann to the fourth, H bar to the third, some lambda 0. Okay, a prefactor that I don't really care what is this. And what is most important, we obtain this T to the third. We can go to experiment. We measure the specific heat of volumes, many of solids, many different solids, and we will obtain exactly this behavior over here. Why it's so different from what we obtain in the Einstein model? In the Einstein model, we always had something which is completely independent. We had 3n oscillators that were independent of each other, and what they produced that even for small temperatures, okay, we need to freeze up all those oscillators. This is why the CV grew fast. Okay, so when we plot in CV as a function of t, what we obtain from what we obtained from Einstein model is a really fast growth, okay, a really fast growth at small temperatures. How fast? It was proportional to e to the beta, h bar omega divided by k Boltzmann T. Okay? It's a very fast growth of the specific heat. Why? The specific heat is defining how fast the energy, average energy, changes with the temperature. Okay? Now we're starting to heat the system. All the different oscillators are completely independent. Okay? So we can transfer this energy to all of them in parallel, right? And all of them start to vibrate really, 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 really fast, right? And the specific heat and the energy grows exponentially fast. We have independent particles. They are all taking this energy, this temperature, this heat that we are putting inside the system. They start to vibrate. The energy of the system explodes. How fast? Exponentially fast. Okay? Yep. No minus. Yeah, you're thinking something like that? Wait. When t goes to 0, this is, so minus. Minus. Okay. Now what happens? What happens in our case? What happens in our case that we have this t to the third. Okay. Where it actually coming from? It's coming from that when we have this flux of heat to the system. Instead of all those different particles that they will start to rotate to vibrate somehow, what we start to see that there are preferred vibrations. Okay? And only those preferred vibrations will take place. So it's not only that one single particle will vibrate and another single particle will vibrate. All the system will start to vibrate somehow, okay, in a coordinate fashion. And this is not intuitive, but this is what exactly gives this t to the third behavior at small temperatures. Okay? This is the big difference between coordinated motion, correlated motion that we managed to solve, and the independent motion of the Einstein model. All right, so this is only the small temperatures. What happens at the large temperatures? In general, we have the answer over here. Insert here omega dBi, solve the integral, and you're done. Okay, and we're looking only in the two limits. First of all, we already succeeded where the Debye model succeeded where the Einstein model failed. Where it failed? At small temperatures, and we got the right answer. Okay? What happens at the high energy temperatures? So the high energies, high temperatures, we need to solve this integral when ud goes where? So the limit of high temperatures ud is h bar omega dBi divided by k Boltzmann T. Omega dBi is independent of the temperature. Okay? So ud goes to 0. Okay? So we're looking on an integral from 0 to u dBi. Okay? U dBi is a small number now. Of u to the fourth e minus u divided by 1 minus e minus u squared du. Okay? This is something that we need to solve, right? Nothing else. We have a prefactor, but the prefactor is exactly the same, right? So it's the same prefactor as we have over here. Now, in this integral, ud goes to 0, so u, all the way, u is much, much smaller than 1. Okay? So when u is much, much smaller than 1, we can take and expand e of minus u as 1 minus u. Okay? The higher the temperature, the better my approximation is. Okay? So I have an integral from 0 to u debye, okay, of u to the fourth. Here I have 1 minus u, okay, divided by 1 minus u to the second power du. Okay. This equals to 0 to u debye u to the fourth divided by u to the second power of 1 minus u du, okay, which equals to an integral from 0 to u debye of u to the second power du. What happens to u to the third power? I neglected it. Okay? I'm only taking the leading term. There are some small corrections. I don't really care about them. Okay? Again, u is smaller than 1. So we obtain that this integral from 0 to u debye of u squared du is 1/3 of u debye to the third power, which equals to, let's go over here, equals to 1/3 of h bar omega debye divided by k Boltzmann T to the third power. All right. This is also nice because when we go back, we have a CV, which is v divided by 2 pi squared of c tilde to the third of k Boltzmann to the fourth of h bar to the third of t to the third multiplied to 1/3 of h bar omega debye k Boltzmann T to the third power. Now omega debye is, we had this long expression, right? What this omega debye is. Omega debye is this 18th something something something. So omega debye is 18 n divided by v 1 over c tilde 1/3. Am I right? Mm-hmm.
Pi squared.
Pi squared. Where was pi squared?
18 and pi squared.
18 and pi squared.
And also c tilde
C tilde to
to the third.
the third.
Not third.
Yeah. This. Yes. All right. Okay. I think. Just a second. I think C tilde was upside over here. I'm going to tell you why in a second. To the third. Because you see d omega, v and c, they are always one in the denominator and one is the numerator. So C tilde must be in the denominator. They are not on the same side. All right, so we got it exactly last lecture, and I think it's C tilde to the third and not C tilde to the minus third. Now I'm telling you why, because when we take this guy inside, okay, we substitute it instead of omega debye. we obtain that CV, look, all of this disappears. You see, this is T to the third, T to the third, K Boltzmann to the fourth, K Boltzmann to the third, so we only left with K Boltzmann. Okay, we are having here n to the 1/3, n to the third, so we have n. Okay, everything else, h bar to the third, h bar to the third, t we already killed. C tilde, okay, this is why I put it up there. It died. This is why I wanted it up there and not down. Okay, pi squared also died. Okay, so we are left, and here we have 6, and here we have 18. So we have 3n K Boltzmann. That's it. Nothing more. Why I wanted exactly this result, I will explain you in a second. Okay, so we basically see that CV divided by 3n equals to K Boltzmann. Now this is also was exactly the same result for the Einstein model. Okay, both of them, the Debye model and the Einstein model, produced CV to 3n, produced the same result, purple. Okay. For large enough temperatures, both of those guys are converging to exactly the same quantity, which is K Boltzmann. And this is absolutely, or should be absolutely right for a system of 3n independent particles. Why I'm telling you that this is what we should get, okay? Because we have something which is called equipartition theorem. So equipartition theorem states the following fact. You maybe learned this in thermodynamics or analytical mechanics. Equipartition theorem states that the kinetic energy average kinetic energy equals to average potential energy when the potential energy is a potential energy of an oscillator, harmonic oscillator. The average kinetic energy equals to the average potential energy. Okay? When I'm telling you this, that what I mean by average, okay? What I mean by average, if we look on a particle, okay, in a harmonic potential, and we track down its energy. So this is time. This is 1/2 mv squared. We're looking on a single particle inside our solid, okay, and its energy, kinetic energy, is fluctuating as a function of time. It's doing something like this. When I average this out, this is the average, okay? This average is going to be exactly, if I measure the potential energy of the particle, record all those small wiggles, record all of those fluctuations, and I will see that the average kinetic energy and the average potential energy are exactly the same. Okay? So this, now, moreover, I know what is the average kinetic energy. 1/2 mv squared average, right? It is always 1/2 K Boltzmann T. Why is that? What is temperature? Temperature, we're saying it's heat. What is heat? If I'm placing my hand on top of an object, I'm feeling that it's cold or it's hot. How do I know it's cold or it's hot? Because the molecules of this object are vibrating and hitting my hand, and I'm feeling pain, okay? And the amount of this pain, this is how I interpret the temperature. The same goes, so basically the molecules of a gas, of this stand over here, are expressing pressure on top of another object, and the amount of this pressure or the momenta they are putting in my hand is the temperature. Okay? What is 1/2 mv squared? Is p squared divided by 2m. This is how I define temperature. Temperature is always the average kinetic energy of the molecule. Always. So what I see from equipartition theorem, that average kinetic energy equals to average potential energy if I have a square potential, if I have a harmonic oscillator. Average kinetic energy is 1/2 k Boltzmann-T. Average potential energy is 1/2 k Boltzmann-T. So in total, for a system of 3n independent particles, the average energy is the average kinetic energy and the average potential energy. So it's 3n multiplied by 1/2 k Boltzmann-T plus 1/2 of k Boltzmann-T. So the total energy, average energy of the system is 3n k Boltzmann-T. Okay? If all the particles, if they can be phonons or the original molecules, if they are all independent, the total energy, average energy, should be exactly 3n k Boltzmann-T. Now, if we take, let's write it over here, du to dt, so Cv equals du to dt, so it's d 3n k Boltzmann-T to dt, it equals exactly to what? 3n k Boltzmann. This is Cv. Okay? So Cv divided by 3n is exactly k Boltzmann. Now this is why I know that my result that I obtained over here from all those extremely lengthy calculations, it is correct. A, it's correct for the small temperatures because I can verify it in experiment. B, it is correct for high energies. Why? Because what I expect to happen in a solid for high temperatures, I expect that all those different molecules will vibrate. Okay? At some point they will be completely, the temperature will be so high that they will be completely independent one from each other. The moment it happens, I can apply my equipartition theorem and I will say, well, if they are all independent, I expect that the specific heat will converge to the Kell-Boltzmann. Okay? It's always like that. If I have 3n independent degrees of freedom, each degree of freedom provides me 1/2 k Boltzmann for the specific heat. I have 3n multiplied by 2 degrees of freedom, so one is kinetic energy, one is the potential energy. So this is why I'm having that Cv divided by 3n is simply k Boltzmann. Okay? Those two results were obtained from the same equation, very long calculation, still holds. Okay? And it holds for the large temperatures and for the small temperatures. Okay? The physics of it is that eventually we managed to do what in the Debye model? We managed to separate the different molecules that are coordinated, and their motion is indeed coordinated, but we described everything in a way of a quasi-particles, of phonons. And those phonons were completely independent of each other. Okay? We paid a price. What price? Our math became ugly and wrong. Okay, we had those long integrals, but it's a technical problem. It's nothing difficult to deal with. Right? It takes a couple of minutes and to keep track of your plus, minuses, and etc. But the result holds for all the ranges of the temperature. Okay? So we do have an independence of the different particles. It's not the molecules, it's the quasi-particles, the phonons. They can either vibrate independently of each other, or they display this coordinated vibration of many and many molecules. By the way, this last result of Cv is actually very nice. Why? Because remember, we already used the specific heat as some sort of a microscope to understand what happens inside a system, right? What is a microscope? I apply light, very strong light. I recollect the light that comes back from the sample, and I say, well, I know what happens inside. CV works in the same fashion, but instead of putting light inside the system, I heat it up. Okay? I can, as a function of temperature, measure CV. Okay? Now, what do I obtain? I obtain so far that for a solid, okay, I have this behavior. Okay? I have a saturation at some temperature. Okay? So I heat up the system and I obtain the saturation. The saturation tells me that now I have 3n degrees of freedom. All those degrees of freedom are completely independent of each other. And they all contribute 1 K Boltzmann. Okay? So it's CV divided by 3n. I can heat it up, and suddenly what I will start to see that I will have another step increase of the CV, okay, and it will continue like that. What this temperature actually tells me, it's called T1. Okay? I heat up the system, I obtain saturation. Saturation means that all the molecules now vibrating independently. Okay, this is the KB. I heat up and obtain another saturation. What happened over here physically? The molecules either started to rotate, so this is, I obtain the increase in CV, and saturation in CV means that some new degrees of freedom entered to the system, to the game, right? And at this point, when everything saturates, all those new degrees of freedom are independent of each other. So what happens? I have molecules. Now I'm telling you those molecules vibrating somehow. What else those molecules can do? They can start to rotate, right? It's another degree of freedom. Or a molecule is not a single atom, single ball that I cannot break. A molecule is constructed from other atoms. So those atoms then start to vibrate internally. Okay? This will add another degree of freedom. So basically, I can have a step-like motion like this. Okay? And each saturation tells me something new that happens inside the system, and the temperature. Now, temperature is equivalent to energy. So at some point, I put enough energy inside the system that I can enforce vibration. I can put another temperature or energy into the system so I can enforce rotations. Right? I can control different behaviors inside the system by heating it up and looking on the behavior of the specific heat. This is why it's an interesting property, because I can heat up the system, study the response, and tell you what happens inside without using a microscope. Maybe I cannot use a microscope. Why? Because it's a bulk. Right? Try and use a microscope. What happens in 4 centimeter depth inside a block of wood? You can't. Right? But by measuring specific heat, you can actually say something about what happens inside. And now with the use of the canonical ensemble, we can also predict the behaviors, and our predictions are quite right. Yep.
What you said about putting your hand on something, and when it's hot, the molecules vibrate and you feel the thing.
Yep.
But when you put your hand on ice, you also feel things.
Yes.
But it's not hot.
So, all right, you're right. So this is already, how your neurons react to some specific. So you, first of all, you can feel heat, right? You can feel something which is cold or hotter, right? At some point, it is actually the hurting, the feeling of that it's hurt to put or keep the system on a surface, for example, which is cold, is due to the reaction of biological reaction of your neuron, okay? Right? So it reacts to heat, okay? It reacts to pressure, but it can also react to cold. And it's a funny way how your brain working, but that's a different story. Okay, so we dealt with Debye model. Now, the last probably model of canonical ensemble. Any questions about the Debye model? Because we are done. No? Bye-bye Debye model. Now we are going to black body radiation. So black body radiation is something that is very, very similar to the Debye model. what is a black body radiation? Now, think of it. What we are trying to solve, we're trying to look on some simple ingredients, okay, build a simple model, and try and investigate its behaviors, okay, under different conditions. Now, the Debye model was a model that is constructed naturally, due to Einstein, naturally constructed from what we know about the microscopics of solids. Now, black body radiation is a slightly different question. The question here is, how can we measure temperature? Okay, how can we measure temperature of something that is located not near us, but really far away? Okay, a temperature of a sun, or a temperature of, I don't know, a fire that somebody started at 1 kilometer from us, and we're looking in a telescope on this fire. Okay, we want to obtain a measure, even a very simple measure, of how the light that we are collecting is related to the temperature of the body that emits this light. Okay? Can there be is there a way or no? Okay? Now, as I told you, I can put my hand on something and measure the temperature. Okay? If it's cold or it's hot, it's hurting me. If it's hot, it's hurting me. So it's really bad measure. My hand over here. I need a better measure, and moreover, it's not that I can go and stick my thermometer inside the sun and say the temperature of the sun is 10,000 Kelvin or whatever. Right? I cannot do this. The only information that I'm getting from the sun is the light that I'm absorbing. Okay? I want to measure my temperature. I'm not touching myself with some thermometers or etc. Just, you know, take a picture of myself with a specific camera and tell you, okay, my temperature is 36.6 Celsius. Okay, so how can we do that, and what is the model? So the original model for light, temperature, and etc. called black body. Why it's called black? It's called black because it's not reflects any light. So if you're looking on one boundary of this body, okay, so usually one imagine it as a closed system, okay, and there's some sort of a radiation, electrical radiation, photons or light that are basically wandering around this cavity. So we have a vacuum inside over here, okay, we have boundary. This boundary absorbs the light. So all the lights that hits the boundary, it's always absorbed, and then after a while some radiation is emitted from the boundary itself. Okay? So usually when we're looking on an electromagnetic wave that hitting a surface, okay, the surface, part of the radiation, part of the wave is absorbed and part of it is reflected. Okay? Black body is called black because all the light, all the radiation is absorbed. Okay? But it's not like a it's not like it's never emitted. After a while, it is emitted from the boundary inside to the cavity backwards. Okay? It's not a reflected light; it's an emitted light that is coming from the black body. Okay? Now, we are assuming that there is some sort of thermal equilibrium between the light, okay, and the body itself, okay, because the body emits energy or emits photons in this case that is related to what? To the temperature of the body. Okay. So this is a neat way to introduce temperature of an object and a photons that are nearby it. Okay, it emits specific photons, emits specific radiation. Okay, and we are assuming that there is an equilibrium between the photons that are hitting the boundary and the photons that are emitted from the boundary backwards. Okay? So the whole process is there's a lot of photons inside. Some are hitting the boundary and are absorbed. Some are emitted from the boundary and wandering inside. And this all goes for a long time. And everything is in thermal equilibrium. Okay. So what kind of waves are going to survive inside this cavity, inside this black body? Standing waves, right? Standing waves, standing electromagnetic waves. Some of them are emitted, some of them are absorbed. So we're looking on a situation where we have a lot of different standing waves that are somehow living inside this cavity, inside this black body, right? They are in thermal equilibrium. So first of all, if we're talking about waves, we know how to calculate what? We know how to calculate the density of states. Great, okay, we already know this. D of omega, right? D of omega is V divided by 2 pi squared. D, what it was? dk to d omega, okay, k of omega squared. Okay? So we know to calculate the density of states, what kind of frequencies those phonons are going to have. It's described by this d omega. Now those are simple electromagnetic waves. So the relation between the wave vector, okay, and the frequency is linear. K equals omega divided by c. And we have only two of them, right? Because it's an electromagnetic wave. Electromagnetic wave, if it propagates in that direction, the oscillations are always perpendicular to the direction of the propagation. So we only have transverse waves and no longitudinal waves. So this part is somehow clear. We know that if we want to treat density of waves, of photons inside this cavity, we know we already calculated it. This part is easy. The other part is, what is the energy? Okay, so A, we are assuming that the energy is the energy of all the different photons that are living inside this cavity. Okay, what is the energy of a photon? H bar omega, right? We know this from Planck. So we have many different photons. Previously we had phonons, now we have photons. We have many different photons, electromagnetic waves. Each of them has an energy of H bar omega. And how many of them? Well, they're independent of each other. So we can say the following thing. The energy of this system, so it's even easier problem than the Debye model, because in the Debye model all the phonons, or we started from a situation when all the particles were correlated somehow. Here we're starting, we have a lot of different photons inside. How many? I don't really know. Many. Okay? All of them are independent. They are not interacting with each other. They are interacting with the body. Okay? They are absorbed and they are emitted. Okay? They do not care about each other whatsoever. What is the total energy of the system? Is the total energy of the phonons. If we're looking on all the phonons that have frequency omega, okay, and we are asking ourselves, let's calculate the total energy as the total energy of the phonons that have frequency omega, 1, right? The total energy, let's call it N1. The total energy of the phonons that have omega 2. The total number of phonons there is N2. The total energy, okay, of photons that have frequency omega 3, there are N3 photons with this specific frequency. Now, I'm saying that the total energy is all the phonons with omega 1, all the phonons of omega 2, all the phonons with omega 3, etc., 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 etc. I have to sum up over all different omegas that are in the system. How many there are omegas inside the system? It's going to be provided to us by this density of state. For one specific omega, okay, for one specific frequency, I can calculate the partition function of all the particles, let's call it Z1 of omega, of all the particles that are contributing, okay, to the total energy, but they all have this omega. Okay, what is Z1? So we can have we can have 0 particles, okay, 0 particles with frequency omega. So it's e to the minus beta h bar omega multiplied by 0. We can have only 1 photon, right? So minus beta h bar omega multiplied by 1. We can have 3 photons, e minus beta h bar omega multiplied by 2, plus etc., etc., etc. So previously I was counting, I was taking one specific phonon and asking what are the different energies of this phonon. Here I'm doing something which is similar but really different. I'm saying let's take a specific omega and ask ourselves what is the how many photons are there with this specific omega. So there can be 0, 1, 2, 3, 4, 5. They all contribute to the partition function for this specific omega. So z of 1, this is again a geometric sum. So this is 1 over 1 minus e beta h bar omega, okay, because I have a geometric summation. And the total partition function, because all the different photons are independent, all the different frequencies are independent as well. So z of omega z, due to factorization, because everything is independent, we multiply all the possible omegas that we have inside the system of z1 over omega. Okay? Previously it was different because I was counting phonons. Here I count frequencies. Okay? Previously omega, there was one specific phonon for one given omega. Here I have many photons for each omega. How many, I don't really know. But the formula stays the same. It doesn't matter what I count. I count contributions to the general energy. That's it. That's all that matters. So it's really important to notice this difference. The difference is slight, but this is really, really deep. Instead of counting particles, I'm counting omegas. Previously, those omegas were the particles, and now, for each omega, I have can have many different particles. Yes.
But omega might be continuous.
Okay.
Shouldn't you want?
Yeah, we're going to use this. Previously, omega was continuous. Yes. So what's the problem? No problem. This is why we developed this formula for the density of states. Okay? Explicitly for those two problems.
I have a question.
Yep.
Yeah, so assuming the Z1 is for one specific
Omega.
yeah,
Yes.
So we are summing over number of photons.
Yes.
It's e to the beta h bar omega
N.
n, which is 0 with.
So here it's 1, right? Plus e to the minus beta h bar omega, plus e to the minus 2 beta h bar omega, right? Plus e to the minus 3 beta h bar omega.
Does the n correspond to the number of photons?
Yes.
Okay.
Yes. N is the number of photons that are having omega frequency. Okay? Now the difference is, previously we had a finite number of phonons. Here we don't know how many photons that are inside. We know that there is some amount of radiation. This radiation is constantly changing. Why? Part of it is absorbed, part of it is emitted. Okay? So we don't have a limitation on the number of photons now. This is why we sound from 0 to infinity. Previously, we had a limitation. The number of phonons was 3n the number of particles. Here it's different. The number of particles, because of this exchange of energy, okay, the number of particles is not constant anymore. Okay, now the moment we have written it in this fashion, and we know that this is d of omega, we are going backwards to the same nasty and lengthy integrals that we had previously. That's it. Because now the system is solved. We know what is z omega. We have factorization. It's easier because previously we had to work extremely hard really hard. You remember those matrices and vectors and multiplications to obtain something that is factorizable. Now we start from a factorizable system, so this is easy. Okay. So if we want to calculate something like, for example, okay, the average energy of the system. Okay, remember what was the average energy of the system? We developed this formula at the beginning of this lecture. So U was minus 1 over beta d2 of log of z. Thanks. Okay? So we know, so if we want now to calculate U, or we later want to calculate specific heat or whatever, okay, we're going to have this formula. Ugly, nasty formula. Okay, so what is this? Is minus d to d beta of, instead of multiplication, okay, we have a summation over all the different omegas. Z of omega is log of 1 over 1 minus e minus beta h bar omega. Okay? And we have to sum over all of them. Okay? We can write it down as d to d beta of a sum over omega, a log of 1 minus e to the power minus beta h bar omega. And this is where the density of states enters. Okay? This is where we take this summation and we say we have an integral. Okay? Because they can be continuous. Right? So U equals d to d beta of an integral, and in a second we will write the limits of this integration, of a log of 1 minus e minus beta h bar omega multiplied by this guy over here. V divided by 2 pi squared. Okay? And let us write this expression explicitly for electromagnetic waves. So there are, so d of omega equals to V divided by 2 pi squared. Is this, it's too low. Let's write it d of omega, d omega. Okay, so this is our integration. Now let's write down the d omega. So d omega is V by 2 pi squared. dk to d omega, okay, is 1 over c. Okay, here I have omega squared divided by c squared, and I multiply it by 2. Why I multiplied it by 2? Exactly. So if this is the propagation of my wave, the polarization is either here or either there. Previously we had 3. Why? Because we had also oscillations in this direction. Now we don't have. Okay, for electromagnetic waves, there are only oscillations or k's that are perpendicular to the propagation of the wave. Okay, this is why we have 2 over here, and they are exactly the same because everything is in vacuum. Previously we had some media, complex media, now everything is fine. All right, so we're here. We can put this inside, and we are having that U equals d to d beta, an integral of a log of 1 minus e minus beta h bar omega. Okay, and here we have V divided by 2 pi squared, 2 over c to the third, omega squared, d omega. And now let's go to the limits of our integration. So it obviously starts from 0. Okay, we do not have negative frequencies; they are all positives. Okay. Previously we had a cutoff. We had here omega debye. This omega debye came from where? It came from the fact that we said, well, this is a physical media. The waves are vibrations of different molecules. There is nothing to vibrate between two atoms. So I have to have some maximal frequency. Because I have a minimal length scale, I have a maximal frequency. Here, I don't have any limitations on the frequencies of electromagnetic wave. Well, we can have extremely large energy. Yes, that's fine, but I actually don't have any limitations whatsoever. And this is related to your question. There is no limitation on the number of photons inside a system. It can be infinitely many. So here we put infinity. Okay. So this is U. Okay. Do you want me to perform all these nasty integrations, or do you want a final formula? Final formula. Surprising. Okay. Let's see what I've got over here. So let's see. We have that U equals to an integral from 0 to infinity after I perform this d to the d beta. V, let's take this out, V divided by pi squared c to the third, h bar omega to the third, E minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega d omega. Okay, very nice formula. Okay, remember my original question. What was my original question in this for all this model? I want a measure of the temperature, okay, given that I have some absorbed light from a distant place, like a star. Okay, or a sun. So what do? First of all, I am saying, well, let's not look on omegas. We developed omegas so far, but let's develop with this expression. Let's make a change of variables, and we will use E, which is h bar omega. Okay? Why I'm doing that, we will see in a second. So when I'm changing the variables to this epsilon, so U equals to what? An integral from 0 to infinity of epsilon, and inside here I have V divided by pi squared c h bar to the third, epsilon to the second, E beta epsilon minus 1 d epsilon. You can say, well, there is nothing different from this representation or that representation. But this is actually a very big deal. Why it's a big deal? What is written over here? U, this is the average energy. Okay? So if, let's assume that I have energy, which is a random variable. Okay? It's a random variable, and I want to compute the average value of this random variable. Okay? U average, it is what? An integral of the probability of my random variable to be U multiplied by U du. 0 to infinity. Okay? This guy over here has a name. This is the probability density function, P of U. What is the probability of having energy U? I'm calculating the average. The average is the probability of having energy U multiplied by U, summing up over all different U's. So, if we look on this expression over here, what do we see? Average U equals to, what is epsilon? U, the energy, h bar omega. So it's U multiplied by something, d epsilon. What is this? This is the probability. Okay? So P of epsilon, d epsilon, is V divided by pi squared C h bar to the third epsilon squared E beta epsilon minus 1. Yes? I'm not missing an exponent. I put it downwards. This is with the plus. Okay? How it's helpful? It's helpful because what do I do with light? What is the light spectrum? So I have a, I don't know, I forgot the name of this device, but I'm absorbing light. Okay, I have a spectrometer, and I'm saying the photon that I now arrived has energy A. The photon that's arrived a second later have energy B. The photon that I arrived 3 or 4 seconds afterwards, okay, have another energy. I can, by absorbing light, build a histogram of all the energies of the light that is coming from a specific source. So by spectral separation, okay, I can actually go and plot from experiments this P of epsilon. Okay? So P of epsilon, P of energy, is something that can be measured. Right? This is something that it's a pretty simple thing to do, but I can measure the energy or the frequency is exactly the same thing, right? Because E equals to h bar omega. I can measure the frequency or the energy of all the photons that are arriving to my device, right? And I can build up the distribution, it's going to be an histogram, of all the different energies that I'm observing, right? So this I'm observing from experiment, okay? And this is what my model tells me. Now remember here, what is beta? K Boltzmann T. And usually when I'm looking on specific light that's arriving from sun or etc., I usually have one specific peak, okay? Only one specific peak. So what I'm doing, I'm going to see where is the maxima here is located. The maxima here is located at the location of this maxima is dictated only by the temperature. Okay? If I'm looking for a maxima, all the prefactors are not interesting, and I'm looking on what is d to d epsilon of epsilon squared divided by E epsilon by K Boltzmann T minus 1 equals 0. Emax. Okay? So what can I do? I can absorb light, build a histogram, and try to fit my model to this histogram. Sometimes it will work, sometimes it won't, but it will provide to me a measure of the temperature of the source. Okay? Can fit it up to my model over here, and from the fitting perspective, obtain the effective temperature that stands in this place. Right? This is how I'm going to look on the stars and at least at some crude approximation tell you, well, this star has temperature 3000 Kelvin. And our star has a temperature of around, the sun is 5800 Kelvin. Okay? I can measure the temperature of a human body. Okay? Or I can build up thermal vision, right? Those goggles that I can use in order to see at night what I'm actually doing, how I'm absorbing light, okay? And I measure temperature and measure movement based on this fitting criteria. Moreover, I don't have to tell you about it now, but we'll tell you about on Tuesday. This procedure is actually, there are mainly two basic claims why the Big Bang theory is actually true. Okay? There are not a lot of evidence out there that we can say, well, that there was indeed a Big Bang theory and how our universe is started. Background radiation and what is called a cosmic background radiation is one of them. Okay? But not today. We'll talk about it on Tuesday. Thank you.